Hello. In this video, we will be showing you how to demonstrate the relationship between radius and angular acceleration with a quick lab using simple objects and the Firefox application. The Firefox application is an app that you can install on most modern smartphones that uses the tools in the phone to collect data for experiments, such as sound waves, magnetic waves, linear acceleration, and inclination. What you will need for this lab is toothed gears/sprockets of varying sizes, a smooth flat ramp of a known angle, and a phone with the Firefox application installed. Remember, if the gears are too thin and don't stand up on their own, try to attach a rod and connect 2 or more gears together so that they are less sensitive and won't fall over. Now it's time for the lab. Position the ramp on a flat surface and use Firefox to take its angle. Next, take one of your sprockets and hold it at a marked distance near the top. Put the phone with Firefox open with the audio scope tab next to the ramp. Now set this recording duration to at least 300 to 500 milliseconds so you have more data to work with. If you wish, you can connect the Firefox app to a computer using the remote access feature to export the data easier. Roll the gear/sprockets down one by one, recording and exporting the data after each trial. Make sure to repeat each trial at least a couple of times so you have more accurate data and less error. Now you have all this data, you have to turn it into actual results. But how do you do that? Well, here's Leo to show you the physics and the math behind it.
To start with the physics, notice that in each dataset there are peaks and troughs for each recording. To calculate the angular acceleration of this sprocket, record each of those times. For example, this peak is at 122.75 milliseconds. You will end up with something like this. So this is one of the trials that was made. Here you can clearly see the troughs and some of the peaks as well. So here are the times in milliseconds in column A marked here. So in column B, the period was found between each time for each peak and for each trough. So this number here, 61.17 seconds, represents the time difference between this cell and that cell. So this is the second peak and this is the first peak. And this is the same for each of all of these other cells. From that, we can find the frequency because we know that period equals 1 over frequency, but since this is in milliseconds, period is in milliseconds, frequency is in hertz, we need to multiply by 1000 to find the correct frequency for each one. So we have the frequency for roughly instantaneous frequency for each time period. From that, we can find the angular velocity because the frequency of these clicks of the sprocket from constant data shown here, the slope is roughly 3.3 degrees. There are 16 teeth on this sprocket. From that, we can find the angular velocity of sprocket at that particular point in time. This is only an approximation because we can't find an instantaneous velocity. However, we can get quite close to that. And from these values, we can find the angular acceleration at that point, or we can just find the change from the angular velocity at the final timestamp from the initial timestamp and dividing it by the time period from the final time to the initial time. This results in an average, or you can just take the average of the angular acceleration, whichever one is fine. An alternative approach to finding the angular acceleration is going up to this point, having the angular velocity, then plotting that as another graph in function of the time at each point. We get graphs like these. This is for the peaks and this is for troughs. Then we can find the best fit line using Google Sheets, trend line, linear trend line, and from that we can find the slope, and that is how we find the angular acceleration in radians per second squared. So we know that the torque is equal to the moment of inertia times the angular acceleration. Therefore, rearranging the terms a bit, angular acceleration equals torque over the moment of inertia. We know that torque equals force times the radius, and that force comes from the friction of the ramp on the sprocket rolling at a distance of r, the radius of the sprocket. And if we assume that the sprocket has the same moment of inertia as a disk, therefore the moment of inertia of this sprocket will be approximately equal to 1/2 mr squared. Canceling the r terms, we have 2 mg times sine of theta, theta being the slope of the ramp, times mu, the static coefficient of friction for the ramp on the sprocket, over mr. The mass cancels out. This leaves us with angular acceleration equals 2 times g times sine of theta times mu over r. From this, we can say that as a hypothesis that angular acceleration will be inversely proportional to radius. In order to measure the angular acceleration, we can first count from the trials the periods from each peak to peak and trough to trough. So in order to find the angular acceleration, we can first find the angular velocity and finding the change of that over time. In order to find the angular velocity at any particular point, we first find the period at that point, find the frequency using the relationship period is 1 over frequency, counting the number of teeth on that sprocket, and using the equation here, angular acceleration equals 2 pi times the frequency over the number of teeth on that sprocket to find the approximate instantaneous angular velocity at that time. From that, we can find the change of the angular velocity over that certain period of time to find the angular acceleration, and measure that to see whether it is inversely proportional to the radius, assuming that gravity, theta, and mu are all constant.
If you followed all these steps correctly, congratulations, you've completed this lab. Just remember, a lot of the info in this video is pretty surface level, so if you want to learn more, I recommend doing your own research on your own time. If your results aren't matching up, that's okay. This is quite the difficult experiment to do perfectly the first time, since there are so many potential sources of error. Just try again, and maybe you'll get it next time. With all that, make sure to like and subscribe, and thanks for watching. See ya!